In this section, we are going to talk about rational functions, p of x over q of x, where we have two polynomial functions, so a ratio of two polynomial functions. And we are going to break them apart in what is called partial fraction decomposition, and then we're going to integrate each of those partial fractions based on their composition, based on what they look like. So let's just start off talking about a few basics. So again, p of x over q of x, we're looking at integrating p of x over q of x, where p and q are polynomial functions. So we're going to be taking an integral, and we're going to have to first look at that rational function and decide if it is in proper form, meaning the degree of the numerator is less than the degree of the denominator. So if that is true, if it's in proper form, then we'll continue in our process. But if it is in improper form, meaning the degree on the top, if it is top heavy, if the degree on the top is greater than or equal to the degree on the bottom, then what we're going to do is actually use polynomial long division to put it into proper form. So again, I always reference this. This is just like a fraction with numbers. If we have 10 over 7, that is in improper form. And so the first thing we do if it is in improper form is we can put it in mixed or proper form. And so what we do is we take 10, we divide by 7, it goes in one time, there's a remainder of 3, and we write that as 1 3/7. If we're working with a polynomial, if we have something like t cubed minus 3 over t minus 1, this is also in improper form. And before we can integrate it and before we work with it, what we do is we do long division, polynomial long division, and we put it into a form that will be in proper form. So we take it, do our long division, put it into proper form, and then we can integrate it. So those are just some terminology that we're going to start with. So that is what we're going to do first. That's the first thing we look at. Once it is in proper form, we have an algebraic theorem that we can use to break it into partial fractions. So let's take a look at that next. Before I show the theorem on how to break up a rational function into partial fractions, I want to just show you why we want to do that. And so let's work backwards. So if we started with two fractions like we have here, so if we started off with just two simple fractions, each has 1 over x minus 2 plus 7 over x plus 5. Each has a denominator that is a linear factor, and we wanted to combine that into one fraction. What we would do is just use some basic algebra, find a common denominator. The common denominator, because these are two unique linear factors, just the product of the two. So here, I already did that work here in the typed up form, and we just expand and we add, and we end up with something that looks like this, 8x minus 9 over x squared plus 3x minus 10. Now, we're going to be going backwards. So what we're going to do is we're going to be starting with this guy. We're going to be integrating, we're going to be wanting to integrate 8x minus 9, and it is not in a form that we can integrate there. But think about where it came from again. Remember, it came from the sum of two, what we call partial fractions. So if we can use some theory to work our way backwards to those partial fractions, which is what I did here, then we can integrate, because think about it. If we integrate those little partial fractions, 1 over x minus 2 and 7 over x plus 5, we can do those pretty quickly just using, it's actually just a quick little u sub on the denominators. I didn't show that work, but we'll show that work in some of our examples. We do a quick little u sub, they become 1 over u and 1 over w, something like that, and we can integrate and we end up with a result that looks like that. So that is why we want to break it into partial fractions. Now, how do we do that? What is the theory that we do to do that? And I'm not going to go through any sort of proof on that theory. I'm going to give it to you. It's an algebraic theory that says that if we have a rational function and we can factor its denominator into what we call linear factors, like the ones we're looking at here, like x minus 2 and x plus 5, either they could also be repeated, linear factors, and irreducible quadratic factors. So we'll talk about that. Then we can break it up into partial fractions based on those factors of the denominator. So let's take a look at that next and then practice this breaking up of fractions. Okay, I am projecting the strategy sheet for partial fraction decomposition that I have provided for you in Canvas. So this strategy sheet will be useful when we're working with partial fractions, when we're working with rational functions and using this concept of partial fraction decomposition to break them apart. So if we have an integral in the form p of x over q of x, where we have polynomials, the first thing we're going to do, as mentioned before, is make sure it is in proper form. So we'll make sure it's in proper form. If it's not in proper form, that's our first step. We'll use long division, that algebraic strategy, and move forward from there. Then the next thing we're going to do is we're going to factor the denominator completely. Now, based on, again, some algebraic theory, it will factor into a product of linear factors. Linear factors are of the form ax plus b, or what we call irreducible quadratic factors, ax squared plus bx plus c. So, quick little note, these linear and quadratic factors could be repeated, meaning we could have more than one of the same linear factor. Let's just suppose we're talking about a linear factor, x plus 2. It could be repeated. We could have, when we do the factoring, we could have x plus 2 to the third power. That would be repeated 3 times. Okay? So we will see some repeated factors. Then this is the theory that we're going to work with. We're going to break that rational expression into what we call partial fractions, applying the following algebraic rules for each of the types of factors in the denominator. Each linear factor will create a partial fraction of one of these forms. So for example, if I have a linear factor, and let's just say it's not repeated, if this r were 1, then we will get one partial fraction of the form a over ax plus b. Now, if our linear factor we're looking at happens to be repeated, say there's 2 or 3 of them, this power on the linear factor is something larger than 1, then it will create our partial fractions. So we'll have the first one will be to the first power plus a constant b over ax plus b to the second plus, and so on and so forth until we get our partial fractions for that linear factor. And then so we look at each of the linear factors, and each one of them will create, based on the power r, will create our partial fractions of this form. So it's a lot of symbols, but we're going to walk through the theory and then practice. Each irreducible quadratic factor, repeated or not, will create a partial fraction that looks something like this. Now, each of these a1, b1, these are all constants, but again, up here I used a, b, c out to z, but because we have lots of constants in this algebraic breakdown, I use the subnotation. So each irreducible quadratic, repeated or not, so say this is to the r power, that could be 1, 2, 3, or so forth, whatever that r is, each of the irreducible quadratics will create our partial fractions when we do the breakdown. And those partial fractions, you'll have the irreducible quadratic on the bottom, and the partial fraction will have a linear term in the top, ax plus b, or a1x plus b1. If we want to use subnotation, if we have lots of factors, then it would probably make sense to use subnotation on our constants. And if it were repeated, then we will have r of those little partial fractions. So I'm going to stop right there. I'll project the rest of it, but that's the part I want to practice on this video. It's just the breakdown, just getting it, applying this algebraic theory just to start off with breaking it down. Once we have broken it down, we will actually find those constants and then plug them in and integrate based on their form. We'll integrate each of those partial fractions, become its own integration problem. That we're going to practice in the second video. This video, I want to just practice taking our p of x over q of x and getting it into its generic partial fraction form, and then we can come back and practice finding those constants and integrating. Okay, so let's take a look. For each of these, notice on the instructions here, I just want to set up the appropriate form of the PFD. By the way, I use PFD rather than writing partial fraction decomposition every time. So we're going to set up the appropriate form of the partial fraction decomposition, but we are not going to find the values. So do not find the values of the constants. We're just going to break these down and use that theory. So the first thing that we have to do, if our factors are, or if our denominator is not factored, the first thing we'll want to do is factor it. What I should actually say is the first thing we need to do is we need to determine if it's in proper form or not. Notice here that the power in the numerator is 1 and the power in the denominator is 2. So my first quick check is that it is in proper form. I do that just visually. I don't actually tend to write anything down. If it were not in proper form, we'd use long division, put it in proper form. So then, once I've verified that it's in proper form, I am going to factor. So I need to factor the denominator. I can't break it down into its partial fractions until I figure out what the denominator is in factored form. So the first thing I do is I get it into its most simplified, most complete factored form. So here I have an x squared plus 4x minus 21. That is going to factor nicely into what we call two linear factors. That will be a 7, a positive 7, and a negative 3. Each of those is a linear factor, and they are each to the first power. And I am going to write that in because that will guide my next step. So each of those is a linear factor. Neither one of them is repeated. So remember, if we have a linear factor for every linear factor, we will have a partial fraction of the form a over that linear factor. If it is only to the first power, then we will have just a single linear factor. It is when this is larger than 1 that we get the repeated, when we have the repeated factors that we get more than one of those linear factor partial fractions. Okay, so let's head back over. We're going to take, notice on the next example, we will have one repeated. So here we have two linear factors. Each of them will create a partial fraction. So this will be equal to a, we'll use a as our constant, x plus 7, plus, and then I'm going to use b because it's a different constant, over x minus 3. And that is how that rational function will break down into partial fractions. Now, we are not going to find the values of the constants on this video, so I'm going to leave it right there. I just want to work on the partial fraction decomposition. Finding that a and that b involves a little bit more algebra. Once we found those, we would then go back to our integral. If we were trying to integrate this function, we'd go back to our integral and use our integration strategies to integrate. All right, let's keep going. So this one happened to come at us already in factored form. So we don't have to go through the factors, but notice this x right here, by the way, would be like an x minus 0. I just want to mention that. So this x is a linear factor, and it is to the first power. I'll write in the one in red because that'll remind us that we do actually have a linear factor, but it's not repeated. This guy is a linear factor, and notice that it is repeated. It's linear, but it's repeated. It's a repeated linear factor 2 times. So it's repeated twice. And then this is a linear factor as well, not repeated. So what that means is that I'm actually going to have 4 partial fractions, 1 from the x, 2 from the x minus 1, and 1 from the x plus 2. So when I write this out, I'm going to start with my first linear factor, which is just x, and I get one partial fraction, a over x. Then my next linear factor, I'm going to use b over x minus 1 plus c over x minus 1 squared. When we have repeated factors, they will create 2 partial fractions in this case, or whatever the r is. In this case, we had 2. So they will create 2 partial fractions. They will be of the form, we will start with just like a single linear factor, not repeated, we will start with x minus 1 to the first, and then we'll have another linear factor, c over x minus 1 to the second. And then we have one last partial fraction from the last linear factor. We'll call that d over x plus 2. We'll put that in parentheses. That was also to the first power. And that is my partial fraction decomposition. So I'll erase that. I'm going to erase some of the notation. That's the partial fraction decomposition. We've got it simplified. We had, again, notice we talked about how there were 3 unique linear factors, but one of them was repeated. That creates those 4 partial fractions. And again, on the next video, we'll talk about finding a, b, c, and d, and then actually integrating. All right, let's take a look at another one. Here we have already a factored form. We would take a look at this just to make sure it's fully factored. This does not factor any further. This is what we call an irreducible quadratic. So we have an irreducible quadratic. It is to the first power. And for a second, you might look at that x squared and you might think that that is also an irreducible quadratic, but that is not. That is actually a repeated linear factor. So remember that x is x minus 0, and this is x minus 0 to the second power. So this is a repeated linear factor, and we got to be careful of recognizing that that's a repeated linear factor, not an irreducible quadratic. So this, though, is an irreducible quadratic. It does not factor. We can see that, I think, pretty clearly. It does not factor. There are no numbers that multiply to 1 and add up to 3. So this is an irreducible quadratic. So we get our first quadratic, and we have two linear factors. So remember, when we have repeated linear factors, we will have a over that linear factor to the first plus b over that linear factor to the second. Each repeated linear factor creates that number of repeated, right? If we had 2, if it's repeated twice, it will create 2 partial fractions. So this was a repeated linear factors, why we have those 2 partial fractions, and again to the first and then to the second power on the bottom. Then we have the quadratic. So for each irreducible quadratic, we will get a partial fraction as well, but these partial fractions will have a linear factor in the numerator. So continuing with my variables here that I'm using for the constants, I used capital A, capital B. I'm going to keep going. I'm going to use C, X plus D. So that gives me 4 constants that I will have to find. So remember, on the irreducible quadratics, this is going to be a linear numerator. So it'll have a, like an mx plus b when I say linear. All right, let's keep going. Let's do one more. Let's do, oh, and I'll project this one more time. So remember, each of the linear factors give us, each linear factor gives us these type of partial fractions, and the irreducible quadratic factors give us these type of partial fractions. All right. Let's head back over and do another one. So let's take this guy. This guy, oh, you know what? I haven't even mentioned as we're going through these. We should absolutely pause for a second and make sure each of these is in proper form. They were already in proper form when we started, but proper form, remember, is where the power on the numerator is less than the power on the denominator. And so I think you can pretty clearly see that on each of these rational functions that we've looked at. Similarly, like on this one, we would double check. It is already in factored form in the denominator, but it is worth, pausing for a second. The power on the top is 2. The power on the bottom is actually 5 because we've got x squared plus 4 to the second power. If I were to expand this all the way out, this would be x to the 4th, and then we have x to the 1st right here. So this would be, we've got basically an x squared over an x to the 5th. So we do know that it's in proper form, but we should always pause for a second and double check that, because if it's not in proper form, we got to put it in proper form. Okay, so we're going to break this guy down. We're going to write this in terms of its partial fractions. We notice here, let's identify the type of factors. We've got a linear factor, so this is linear. Here we have a irreducible quadratic. X squared plus 4 does not factor. It's a prime polynomial. So this is an irreducible quadratic, but it is repeated. So notice that it's repeated. It's repeated 2 times. So when I break this down, I know I have one linear factor. So that would be a over x minus 3. And then I have 2 irreducible quadratics. Their denominators are going to be x squared plus 4 to the first and x squared plus 4 to the second. So remember, anytime you have a repeated factor, quadratic or linear, however many times it's repeated, that's how many partial fractions you'll get. And the power in the denominator on those partial fractions will start at 1 and go up to whatever the r value is here, of however many times it was repeated. Now the numerator, since these are quadratic, these are repeated irreducible quadratics, the numerator of each of these will be a linear term. So we can't actually start with a because we already used a. So let's start with capital B, x plus c, and then dx plus e. And that's how those will break down. Now we will have to spend the time in the algebra to find each of those constants and then integrate, if we're trying to integrate this function, integrate by the form of each one of those individual partial fractions. But that is the process for breaking it down. That's the algebra for taking these and breaking it down. So I know there was quite a few that we just did. I'll get 3 of them on the board. So just remember, we factor completely the denominator. Oh, check if it's improper, then factor the denominator completely and break apart the rational function into a series of partial fractions based on that algebra. So for each linear factor, we get a little mini fraction, a partial fraction of the form a over that linear factor. If it's repeated, we would get more than one of those. And if it's irreducible quadratic, it will factor into the form ax plus b, a linear term on the top, over the irreducible quadratic on the bottom. And if the irreducible quadratic is repeated, like in the last one, then we will have more than one of those terms. Okay, so this video was just practicing with the algebra. Let's head back and just project that theory again. Looks like it went off my screen there. All right, there's the algebraic theory again projected. We are going to spend the next video working on the latter part of the process. So finding those, actually going in and figuring out what are those constants and then integrating it. So I'll show you guys some theory and some strategy for finding those constants. It's really just a lot of algebra, and then we'll talk about how to integrate based on the form of each of the partial fractions. So that's coming, so stay tuned for that video next.